Hello. Okay, good morning, everybody. I'm here to talk about Express Backbone today. What is Express Backbone? Express Backbone is Facebook's own SDN backbone. So for the rest of the talk, it's kind of divided into 4 sections. I'm going to first go over some of the motivations of why we want to build this backbone. Then we're going to talk about the network design. And then we'll dive into how traffic engineering is done in this network. And finally, we'll share some lessons that we learned. Facebook has multiple data centers in the United States and in Europe, and these data centers are connected through a WAN, a wire area network that we refer as the backbone. This backbone network carries 2 types of traffic, machine to machine and machine to users. We also refer that as the egress traffic. In recent years, machine to machine traffic has increased quite rapidly, and it actually has outpaced our egress traffic. And this is fueled by applications like video and data analytics. And it's getting to the point where we're starting to see that no vendor can actually meet our future demands through vertical scaling anymore. We need some solution that can scale, both in terms of number, site, and capacity. Another reason why we actually want to build a new backbone is flexibility. So in terms of vendor gear for traffic engineering solution, RSVP TE is kind of the only game. In Facebook, we also like to try to experiment and build new things. And finally, we like to move fast. And by moving software in-house, that kind of allow us to do that. So about 2 years ago, we actually decided to build a brand new backbone that carry all the machine-to-machine traffic. So what did we do? Well, in this example, we have 3 data centers, A, B, and C. We decided to connect them through using commodity switches. Then we replicate this topology 3 times and create 4 parallel forwarding planes. We use our own OpenR routing protocol on this network, and we incrementally onboard the traffic using BGP injection. You use S-Flow for traffic estimation, and finally, we add a traffic engineering controller to steer traffic. So it's kind of busy, the lines everywhere. I'm going to go over all these items in greater depth in the rest of this section. EBB has 4 independent and identical forwarding planes. The fact that they're independent provides a very natural 4-way active-active redundancy. In this example, we see that router A in plane 1 is disabled. Traffic through that router will automatically be withdrawn, and all traffic to and from data center A will flow through the remaining 3 planes. Please note that for traffic between data center B and C, the 4th planes remain available. We can also use this architecture for incremental change and software canary. The way it works is that we'll drain the entire plane. And by drain, I really mean detouring all traffic so there's no more traffic going to any of the routers in that plane. And once that is done, we can do maintenance or upgrade. For example, replacing line cards or installing new software. We can also do canary of both software and hardware. That's done by just simply doing the upgrade to one of the planes. We run it for a period of time. If we run into any kind of trouble, we'll simply drain the entire plane and roll back. And if the upgrades is stable, we'll deploy it to the other 3 planes. The fact that these 4 planes provide nearly identical traffic and identical topology provide a natural mechanism for conducting A/B testing. For example, suppose we have 2 algorithms that we want to compare. We can simply run the new algorithm on plane 1 and the existing algorithm in the other 3 planes and compare the traffic behavior on the network. And we'll have an example about this later. For IGP, we use OpenR. OpenR is Facebook's own routing protocol that we announced in last year at Scale conference. It is extensible. For example, it has a distributed key value store where all onboard agent can use to distribute its own information among all agents on the network plus the controller. It's also in-house, so we can get feature and bug fixes much faster than going through vendor. OpenR runs as agents in all EBB routers. We also use this for LSP failover. In fact, EBB is the first production network where OpenR is the sole IGP. Now that we have a network with routing running, we want to onboard some traffic. The amount of traffic that needs to be onboarded into EBB is huge, and it cannot be done abruptly. So in order to minimize potential disruption to services, we need an incremental mechanism, and that is done through BGP injection. So we have an existing data center, A, and it goes through some data center switch, and it connected to the existing backbone, which we call the classic backbone. So you see data center switches connected to the CBB router, and there's some traffic, and now we have EBB routers with no traffic. What we do is we have a configuration containing all prefixes on all sites that we want to onboard. A BGP injector will read this configuration, and then it will establish BGP session with all EBB routers. Well, after that, we start to inject prefixes into these routers, and then the EBB routers will start advertising these prefixes to data center switches. And traffic towards those prefixes would then be switched over into EBB. We can incrementally update the configuration and incrementally onboard more and more traffic using this mechanism. We can also quickly fail back by just simply withdrawing those routes. Once we withdraw the route, the advertisement will stop, and then the traffic will fall back to the classic backbone router. In fact, we used this mechanism in the early day when there wasn't enough capacity due to fiber cuts. We also have a redundancy mechanism through AS path prepend. The way it works is that we run multiple instances of the BGP injector, and they each advertise duplicate routes using different AS path. And so there will be duplicate path in the data center switch, and if, let's say, the BGP injector on the left fail, its route will be withdrawn, and the route injected by the instance on the right will then take over. So now that we have a network with routing and with traffic, we're ready to do some traffic engineering. Traffic engineering is done by the controller, and it consists of 3 steps: collection, decision, and execution. We first start by collecting a network snapshot. That is done by reading a network configuration that describes the desired state of the network. Then this state is override by the live topology provided by OpenR running on all planes. And we create this network snapshot, which is the current usable topology. Then we have a traffic matrix that demands all traffic demand between all sites in the entire network from the S-flow collector. These two are fed as input to the path allocation module, which is an algorithm that devises a strategy to carry the current traffic demand using the current usable topology. It will output a list of label switch path, or LSP, and this collection of LSP that connect all sites we refer as the LSP mesh. The LSP mesh is then fed into the driver, which will then distribute these LSP to this LSP agent running in all routers. An LSP agent will convert these LSP into platform-specific network objects and program them into the routers. And that's how traffic engineering happens. So how do we do traffic estimation? This is done through S-flow. We have a S-flow collector which collects S-flow from all routers. In this example, we have bidirectional traffic between data center A and B. And S-flow samples are generated at router A and B. So S-flow sample contain IP header of the original packet, and it also contains other information like source and destination interfaces. Here's an example of 5 S-flow records. Then these are the fields that we really care about: source and destination IP addresses, the DSCP, and the packet length. And I have a bunch of fictitious IP address, and the third octet, I actually encode a site number where 1 is A and 2 is B. So what we do with these samples is that we classify them into sites. And we use the same prefix configuration that we use in BGP injection. So we simply build a classifier to map all the prefixes back into site. And then we aggregate them based on a source and destination site pair and DSCP. We do this aggregation periodically to get a byte count between these sites per unit of time, and then from that we can get an estimate traffic flow between all sites. And the collection of all those entries is what we refer as the traffic matrix. So now we have the topology and we have the demand. We're ready to do some path allocation. I will use an example to illustrate how this is actually done. Imagine we have 3 data centers again, A, B, and C, and they're connected by a 100 gig link with roughly equal RTT. And suppose we want to carry 125 gig of traffic from site A to C. Using traditional IP routing, this is impossible because they'll take the direct path and 25 gig will be dropped. But with MPLS-TE, we can actually do this. And the way it works is that we first take the demand and divide it into a number of LSP. And in this example, I would just simply pick 5. So we're trying to carry 25 gig of traffic per LSP, and we need to find path in this network so that we can carry all of it. So we first create primary path, which are capacity constraint. What that really means is that we need to find a link. We need to find a path where all links have at least 25 gig, then we can lay it at LSP. So the obvious choice is to simply put LSP in the direct link between A to C. So we did that for the first LSP, and now we have 25 gigs allocated. We repeat this process 2 more times on the same link, and now we have 75 gigs already allocated. At this point, we'll stop because we want to intentionally create some headroom to address bursts. So traffic estimation includes some smoothing, and when you have smoothing, the burst actually gets smoothed out. But that doesn't mean that it doesn't happen in the actual network, so we want to create some headroom for those bursts so we don't drop. Now, we close this direct link. We can still go through a longer path through B. And that's exactly what LSP 4 and 5 will do, that they will simply take a 1/2 path, and now we have a solution where we laid all 5 LSP, we carry 125 gig of traffic from A to C using only 100 gig length. The second thing, next what we're going to do is we want to create some backup LSP in case the primary LSP goes down because some links is down. Backup paths are maximally diverse, and what it really means is that we will simply find a path that goes from the same source to destination site without using any of the link that is in the primary path. So in this case, LSP1 go directly from A to C, so the maximum diverse backup path will simply take the 1/2 path. We repeat this process for all site pairs. For every single entry in the traffic matrix, we repeat this process, and we have a collection of LSP connecting all sites, and that is our LSP mesh. We repeat this process for every traffic class. Traffic class is marked by DSCP. Every traffic class has its own unique set of DSCP, and that's actually why we have a DSCP in the traffic matrix. Now, what I describe is, what the algorithm that I just described is actually something known as CSPF, Constraint Shortest Path First. It's a very popular traffic engineering algorithm, but it's not the only one. There are many other algorithms that can do path allocation, and another algorithm that is very popular is called multi-commodity flow, or MCF. Multi-commodity flow actually is originated from operational research, and it uses some sort of optimization technique. In this particular, we actually implement a variation of MCF trying to optimize the headroom. Remember, we need to keep some headroom to absorb the burst, so we actually use MCF to maximize headroom on all link. Now, earlier we also say that we conduct experiment on the network, and this is an example. So about 3 weeks ago, we actually conduct an experiment comparing MCF against CSPF. And the way it's done is exactly how the earlier slides depict. We run MCF on plane 1, and we run CSPF on planes 2 to 4. So what you're looking at is at the actual link utilization of 2 parallel links connecting 2 real sites. And there's a bunch of color lines. Each color represents the link utilization of those links on each plane. So color blue is that of MCF, and the other color of green, yellow, and orange represent the traffic run by CSPF. So you see that the other color, all the non-blue color, kind of bunch up because they're running the same algorithm. They have the exact same LSP mesh, and they therefore have very similar traffic behavior. While the blue line kind of sticks out, and it looks very different from everything else because it uses a different algorithm, so it has a different LSP mesh. And you can see the difference in behavior. CSPF, like you can focus on the orange line, actually, it load up most of the traffic on one link. And it's because that link has a slightly shorter RTT. So CSPF trying to use the shortest path, just keep putting traffic on it, while there's very little traffic on link 1. MCF, on the other hand, has the ability to load balance between two links and roughly does a 2-1 split. There's roughly 2/3 of the traffic running on link 1 and about 1/3 of the traffic running on link 2. So here's an example where we say we want to be able to try out new algorithm. We implement 2. And we say we want to run A/B testing, and we actually conduct it. And we can confirm through experimentation and actual data that it does exactly what we thought it does. Now we have an LSP mesh. We need to program them into the router so that the traffic engineering actually happens. So here's a carryover from the previous example. Path allocation allocate this one particular LSP, this LSP1. Primary path go directly from A to C, and backup path take the one-hop path, so we go from A to B and then to C. We use segment routing to actually for our data path. So what that means is that we take these paths and we convert them to a label stack. So for primary, we just have a null label, and then for the backup path, we have an extra hop, so we have one more label. And segment routing allows us to program the label only at the source router. So there's no programming at intermediate router. It simplifies our mechanism and makes it more robust. These label stacks are then delivered to the LSP agent running in each router. And then the LSP agent will convert them into the platform-specific network object. Every vendor implements MPLS tunnel differently, so we just use the SDK and program it. Now, we repeat this process for every single router, and notice that only the driver needs to talk to the LSP agent. The LSP agent do not need to talk to each other. So after the LSP are programmed, the LSP agent are responsible for failover. It does this by continuously monitor and react to topology changes. So in this example, we have an LSP that go from A to B to C. What happens if a link fail? Suppose link B to C fail. Now at this point, this LSP doesn't work anymore. We're black holding traffic. What will happen is that OpenR running in router B will will detect the link is down and send an update to OpenR agent running in router A to notify the topology change. LSP agent will then get a notification from the OpenR, and it will program the backup label stack into the router. And then now we switch over to the backup path, and that's how failover happen. Now, in the event that even the backup path itself has a downlink, the LSP agent will simply remove the LSP entirely, and we fall back to IP routing for the moment. So some other software aspect of a controller is very flexible. We can create almost any kind of traffic engineering scheme, and we demonstrate it by creating 2 of the more popular algorithms. Every plane and every traffic class can run a different algorithm. In fact, even the driver can run different, can be customized per plane. So for example, we can actually have one plane running one vendor's gear and another plane running a different vendor gear. When designing the controller, we try to use only the most commonly available features among vendors so that to minimize, to avoid tie down to a specific platform. So now, what are some of the lessons that we learned? There are 2 lessons that we learned that I kind of want to share with you guys that kind of stick out quite a bit. The first thing is about software management. So an SDN, unlike a traditional network, has a lot more software components. We have controller, injector, collector, we have agents. There are actually 11 packages that we need to maintain running on all router. And all these extra software require great overhead of managing them, just upgrade configuration. And initially, we tried to manually upgrade these packages, and it was a nightmare. In fact, we actually have an incident where the failover failed because we have a typo in the router name. So in the earlier day, the router name actually has to be passed into the agent by manual configuration, and there was a typo. So when the link went down, the agent didn't think it was its link went down because it's a different name. So we have incident like that, and we learn from it. So we try to simplify things. The different use cases, there's provisioning, there's configuration, there's upgrade of software, and we simplify all of them in a single rebuild operation. That no matter what's the state the box was in previously, we simply rebuilt it into the last known good state with the latest software and the configuration that we want. We then automate this rebuild operation so that we can do it per plane. And now the operation boils down to we drain a plane, we rebuild every router in the plane, and then we undrain it. And this whole process is now runs in about 25 minutes and no human intervention requires. The second lesson that we learned is that manual debugging is nearly impossible. Trying to debug this thing through CLI is actually time-consuming, and it's very difficult because the controller reprogram all network objects quite frequently, and it also creates a large number of network objects on the boxes. So what we find out so the troubleshooting was really, really difficult. And then we find out that a large class of these problems occur because there's an inconsistency between the desired state in the controller versus the actual state in the routers. So we develop a set of validation that will reconcile the router states against the controller state. And these validations are run as periodic audits. They can also be manually invoked on demand through a CLI tool for interactive debugging. We automate our fault detection mechanism using NetNorrent. It's another Facebook technology that we announced previously, that it sends traffic throughout all paths in the network and continuously monitor when there's any downlink, and raise an alert if it detects some path is not being reachable. Once we find some fault, we also have an MPLS trace route agent running on box that can test all the LSP and trying to isolate which LSP is dropping traffic. It can also help us to find out which segment is broken. So what did we get out of all these? Well, the rollout of software is now pretty simple. It just basically, we just select which plane we want to rebuild and just incrementally roll things out. Drain is fast. We don't have to do LSP reoptimization like we do in RSVP. As soon as we notify that the new topology and controller reprogram, drain is done. There's also some performance win. The failover is quite fast. And typical reaction to topology change, whereas through any kind of fiber cut or maintenance drain, is typically sub-second. In fact, it's typically done about in hundreds of milliseconds. We also get some real-time visibility of the LSP path hop. This happened because the LSP, instead of being negotiated among routers, is centralized designed by the controller. So we can just simply query the controller for what is the expected LSP mesh running at the moment. We also archive all these LSP mesh for historical analysis. We also have a S-Flow collector that has the global view of the traffic demand. And we can use this global view of the traffic demand to correlate that against the LSP mesh for the network. And we can use these two information to study the effectiveness of the traffic engineering algorithm. For example, what traffic pattern result in what mesh, and if it doesn't do a good job, we can find out why, and we can try new algorithm to address it. We can also use these information for capacity planning as well. And finally, the last class of win is flexibility. We're able to build new types of traffic engineering algorithm. In fact, we can implement a very large class of traffic engineering algorithm. The multiple plane allow us to do A/B testing, which allow us to verify whether the traffic engineering algorithm is effective or not. And finally, by moving all these software in-house, we are able to move fast and iterate quickly by trying new idea, bug fixes, features. So in 2 years, EBB went from a concept to reality. EBB is now carrying a lot of traffic, and we learned a lot from just operating this software-defined network. We are now expanding to many new sites, and we're turning up a lot of capacity, and it has been a really fun journey. Thank you.
So just wanted to open up, so after every speaker, we want this to be interactive, right? So please, if you've got questions, and I think folks are going to run around with mics. Thank you very much, folks from FN Tech. If you've got questions. We've even, if you heard some loud cheering over here, a bunch of the EBB team folks, you want to stand up? Just, this is the loud heckling section over here. Don't be shy. Okay. Great, so questions.
Hi, great presentation. So a few questions. One, provision killer space is orthogonal to effect binding. How do you bind your effects to the tunnels?
I'm sorry, can you repeat that?
You need to get traffic into the tunnel, otherwise they need to be resolvable, right? So you need to set up next hop according to type of traffic you would like to send over a particular tunnel.
Oh, how do we funnel the traffic into the MPLS tunnel? We program static routes.
You said that you're using DSCP to create kind of artificial classes. Are you using DSCP values to label next hops?
I'm sorry, I'm having really
DSCP values?
We use DSCP value to classify, to decide which mesh it goes into. So there's some PBR programming to say that you know, this DSCP for this prefix go into this particular next hop group, for example, right?
Second question, data modeling. You've been talking about comparing intended state to operational state. You didn't say anything about how you do it. Do you use YANG? Do you use anything else to compare leaves, values and leaves?
Sorry, I'm sorry.
Are you using data models to compare intended state to operational state?
So the validators actually is it's just a bunch of Python script that issue like we have like we use Thrift for our RPC. So these agents actually they all have API. So the validator is actually just a bunch of Python script issuing this API and then query the state. So we have query from the controller and we query from the LSP agent. And then we just simply compare them to say, hey, I'm supposed to have this label stack program. Does it really exist in the router? And if it doesn't, there's a problem. Or something like the link on this router is down. Is the controller still expecting this link, think this link is up? So that's actually a pretty common, I would say half of the problem that we run into is really because the topology, the controller think the network has versus the actual topology are not the same. But in terms of like how it's done, it's actually just Python script issuing API calls against all these different entities.
We got another question over here.
Hi. What's the traffic, the S-flow sample rate that you do?
I'm sorry. But
the S-flow sample rate?
The sample rate, we sample once every 30,000 packets.
Once every 30,000 packets?
Yeah.
Thanks.
Hi. How physically diverse are your 4 parallel backbones? Are you running them on different physical facilities, or are you running each one as a different color through a DWDM system?
So I think so we do have the 2 backbone. You know, they share some fiber, but there's also some diversity about that. It's kind of a mixture. To the actual extent, I would actually say that you should probably talk to the network folks like Miguel and Mark there would probably be better to answer that question for you. So I'm the software guy.
Got a few more over here. You want to just say it, and then we'll repeat the question?
How do you prevent misbehaving services from flooding the network? Do you impose quotas on them?
So we have other mechanisms to kind of like control the ingress of services into the network as well. So that part wasn't talked about. It's only 25 minutes, so.
We got time for a few more questions. I see some folks over here. I don't know where the microphone went, but.
I'm sorry, can you? So the label stack is, so the translation from just like a site-specific description to the label happens in the driver, which is part of the controller, but the actual programming of the label stack is happening in the LSP agent. So that's through some sort of SDK provided by the vendor. So.
Yeah, hi. I was interested in knowing if there is a comparative study that you guys published outside between CSPF and your commodity algorithm. Just a point that, the CSPF depends on how you express the constraints, so it just sounds like you could achieve the same behavior. And the second question was on your fault, on your dealing with your faults on fiber cuts and stuff, so it's sub-seconds. Is that mostly based on your controller reacting to it? And would you ever be able to get to like 100 milliseconds for applications, networks, where they have to deal with video and stuff? Thank you.
Yeah, so the question about like, can we just use tune CSPF to do what MCF does? I think that's true to a certain extent, right? Like in terms of maximizing network flow, theoretically CSPF converge to that of an MCF solution if you use infinitely small LSP. Of course, it will take infinitely long to run it as well, so that's kind of a problem. So I think MCF is an easier way to maximize that behavior because you have an objective function and this thing is known to optimize it exactly. So I think it's a little bit easier MCF is theoretically optimal and cannot be beaten. Now, due to some implementation loss, it's not exactly implement the exact optimal solution, but it's pretty close. So that's my first question. I kind of forgot the second part, though. You have a second part to the question? Sorry.
The second part was about the sub-second failover times.
So sorry, yeah. So that's important. Actually, what we do is the design philosophy of overall EBB is that we want to make the decision centrally, but the execution of the decision was done locally. So it's kind of a centralized distributed architecture. So the controller make all the decision for the entire network, but the actual execution of the path is done by the LSP agent. The controller is never involved. So that way we can react quickly to like topology changes or anything, and we can still kind of get a global view of what is going on in the network. Does that answer your question, or?
We got time for maybe one more question.
Yeah, actually, yeah, you mentioned boxes which are there, right? Which runs the OpenR protocol and also the LSP agent. I'm very curious to know, are these boxes, if they're vendor boxes or something, we have to modify the boxes to run those protocols, or it's your own, or?
So
the LSP agent and OpenR, for example.
The LSP agent and OpenR we wrote it ourselves. So we just build these agents and run them on vendor gear.
Oh, one more there.
I have a question about the controller. So you have multiple data centers, they are connected. So as the data centers grow, right, so you have a full mesh connecting. There's no hub and spoke topology as I see. So how does your controller work? Is it like sitting in one of the data centers, or is it that's also distributed across it? And how it just like monitors the state?
Sure. So the controller actually just a C++ program, and it's dispatched just like a job in Facebook infrastructure. We have our own job scheduling and deployment infrastructure, and we deployed it, and it just popped up. We can choose preferences, but it can automatically fail over if, let's say, there's some fiber cut and one of the data centers cut off. Our infrastructure will automatically migrate the job and run in a different data center.
All right. Well, great. Thanks again, Henry.